How can individuals somehow participate in a group in an organized and harmonizing way? That'll be our theme in my session this morning. It's actually quite a big mystery in many branches of science. And I think it has implications for governments and societies that I'd like to discuss with you. So first, in terms of the scientific context, let me give you a few examples to keep in mind. Individuals can be people, as we just saw in the case of our synchronous applause, but the individuals that I'll be speaking about could be other sorts of entities. And our issue here is, can we predict what a group will do if we know how individuals behave and how they interact? So the individuals could be, for example, atoms. Consider the DNA molecule. The DNA molecule is made up of thousands of atoms. Individually, no atom stores the secret of life or the secret of heredity, but somehow collectively put those atoms together into the double helix, and now you have the most important molecule ever made. Or think about the cells in the immune system, or in the brain. How about those? Brain cells. No brain cell is conscious individually. It's only when you put something like 100 billion brain cells together and have them interact in the right way, electrically and chemically, that you can get feelings, emotions, memories. These sorts of amazing emergent phenomena that occur when you put enormous numbers of individuals together and let them interact collectively are, I would say, the greatest unsolved problem in virtually every branch of science today. That is, how do we go from understanding individual units to groups? It transcends the examples I've mentioned of cells and atoms. Of course, you can think about this at every scale of organization, from animals in amazing herds and flocks and schools of fish, or societies that have organized themselves. Actually, it seems to be a theme running through this meeting. I was delighted yesterday to be at a session on global well-being and happiness. And the term happiness to an American like myself, we often think of that as an individual issue, that we are told in our Declaration of Independence that we have the right to the pursuit of happiness. But it's often taken to be something that each person should pursue on his or her own. And the interesting point that came out in yesterday's session was that actually happiness is very much a social phenomenon, that people's well-being and happiness depends on their interactions with their fellow citizens. And so we can help each other be healthier and happier collectively. It's not just up to us individually. Well, so as I say, this is a great unsolved problem in science to understand the behavior of a group given the behavior of the individuals and the interactions between them. It goes by the name of complex systems. You have probably heard of the subject of chaos theory that was popular in the 1980s. In the 1990s, chaos sort of evolved into the subject of complex systems, which is what we'll be discussing today. And roughly speaking, the idea is that a complex system is made of many parts, interacting usually in relatively simple ways. And what makes the subject so fascinating scientifically and mathematically, and the reason I think it has so many implications for society and government, is that all kinds of puzzling, counterintuitive, unexpected phenomena occur at the level of the group that you would not see at the level of a single individual. We have a common sense expression for that. People know that the whole is greater than the sum of the parts, because there can be synergies among the parts. There can be cooperation or unity or harmony. But mathematically and scientifically, this has been a perplexing issue to try to figure out how to understand these phenomena that occur at the level of the group. The reason being that in science we use a strategy that is called reductionism, where we like to break complicated problems into their simplest parts and then analyze those parts. For instance, the scientists that do neurology, the study of the brain in neuroscience, think the brain is too complicated. Let's study an individual neuron or an individual synapse. And that's fine as far as it goes, and we've learned a tremendous amount from that. But now the task for science in every field is to put the parts back together and try to understand the whole. And that's what complex systems is all about. So what I'd like to do then in my discussion with you here is show you some examples of where I think some of the insights and lessons from complex systems may hold implications for society. These are, I would say, think of these as mental models. These are little metaphors or analogies. This is not rigorous prediction. These are things for you to think about and contemplate. I think they're suggestive. So the first one that we've done in our own little experiment here was the phenomenon of synchronization. But if you think that the synchronization we performed in this room depended on the sensitivity of the members of the audience, let me show you an example where entities can synchronize even though they are not even conscious. In fact, they're not even alive. They are inanimate metronomes. Now, what I'm going to show first is a video of metronomes that are acting in their individualistic fashion, doing their own thing. As you can see, they didn't manage to organize themselves at all. They clapped, sort of like the way you clapped initially. There was no tendency for them to self-organize, and they didn't. They couldn't feel each other. They couldn't communicate. But I don't know if you noticed, but in that video, they were on a wooden platform, and in front of the platform were two empty, probably Coke or Pepsi cans. And what you're going to see next is what happens if we lift up the board with the metronomes on it and put it on top of those empty cans. And keep your eye on the board. You will see that the board rolls a little bit from side to side due to the ticking of the metronomes, and it provides just enough vibration for them to feel each other and watch what happens. And also listen to what happens. It's not just a matter of seeing. You will hear the difference. Also, I would like you to pay attention to one particular metronome that may remind you of some people you know, in the sense that when everyone else is coherent and doing everything in harmony, there is one stubborn outlier. Now, if you think they're synchronized, watch that second one from the left. That looks better. But did you see what that second one is doing? Also, notice the way that the wooden platform is moving a little bit side to side. Finally, they are synchronized. So those inanimate objects have self-synchronized just through vibrations, the tiny vibrations they put in that wooden platform. Now, if you think this is all sort of strange, and why is this mathematician invited to our conference, I don't blame you for that thought, but I'd like to show you that there really are very serious real-world implications of the phenomenon you just witnessed. Consider the Millennium Bridge in London. It's a magnificent structure. I'm sure some of you have walked over it. It's very pretty. Footbridge that goes from St. Paul's on one side to the Tate Modern Art Museum on the other side of the Thames. It was the first new footbridge across the river in 100 years. It's a magnificent, modern, minimalist structure. And on opening day, June 10th, 2000, to commemorate the millennium, of course, the Queen of England was there, the BBC was there, 80,000 people showed up to walk across this magnificent new structure. And as you'll see, something completely unexpected happened, the sort of thing that often does happen when groups get together. Watch the way the people are walking on the bridge, and also keep your eye on the bridge itself. You'll see it wobbling a little bit sideways. The people almost look like they're trying out for a Monty Python sketch with the Ministry of Silly Walks. Do you see that they're rocking side to side in step? And now look at the cables on the bridge. You'll see them swaying sideways too. So the Millennium Bridge, this was a serious problem. In fact, the bridge had to be closed for 2 years while engineers were very concerned. Could the bridge fall? Could it collapse? Could people be hurt? And what was causing these wobbles? This was a very peculiar phenomenon, not the thing that you may have heard about where when soldiers are marching in step across a bridge, they are told to break step so that they don't cause the bridge to resonate. This is not that phenomenon. These are just ordinary people, pedestrians, walking, who spontaneously synchronized, like you did when you were clapping your hands, or like the metronomes did when put on that platform that could move sideways on the soda cans. Somehow the people synchronized spontaneously while the bridge was wobbling. And the question was, what was causing what? Did the wobbles cause this crowd synchronization, or did the crowd synchronization cause the wobbles? Did you also notice the way the people were walking? I mean, I don't know if you really could see it in the video, but they sort of adopted a walk with their feet spread wide. And picture yourself being on like say, a train that's moving fast and wobbling, or maybe on a boat, a little rowboat that's wobbling. People will walk like this to try to steady themselves. And what was unexpected is that this kind of motion, to get in step with the bridge and feel more comfortable, made the bridge's vibration worse, because inadvertently the people were pumping energy into the bridge at the frequency of the bridge's sideways motion, which caused more people to walk like that, and then you saw the whole crowd was rocking side to side in sync. So the engineering firm, while the bridge was closed, investigated what was happening on the bridge by doing the following experiment. They put their own employees on the bridge and had them walk in greater and greater numbers. You see the blue curve, which starts at 0 and then rises to 50 people on the bridge for a few seconds, maybe about a minute. And the red curve is showing how much is the bridge moving sideways. Notice that as they put 50 and then 60, climbing this staircase of more and more people, the blue curve, the bridge doesn't really move until somewhere, suddenly, between about 150 and 160 people, that red curve takes off exponentially, and suddenly the bridge is really moving. So there was some kind of critical phenomenon happening that in science we would call a phase transition. That once there was a critical number of people on the bridge, it was enough to spontaneously cause both the synchronization and the wobbling. Phase transitions, if that term is unfamiliar, you should think of something like water, which is made up of many individual molecules. And as you cool water by lowering the temperature, it remains liquid until you reach a critical point called the freezing point, when suddenly the whole structure changes and the molecules do something that could have never been anticipated unless you'd experienced it, which is that they form a rigid structure, the solid block of ice that we're all familiar with. So phase transitions can occur in human behavior, as we just saw in the Millennium Bridge. Now, why is that important? I mean, why is any of this important for governments or societies? I'd like you to think of a few possible metaphorical lessons from the experiments we just did, from the metronomes, and from the bridge. First of all, when the interactions are weak, you tend to have individualistic behavior. When you were clapping initially, you didn't have any incentive to get into sync, and you didn't. Oh, yes, and also with the metronomes, the same thing. When the wooden platform was just on the table, the metronomes were not able to communicate either. They couldn't really feel each other's vibrations. It was only when they were placed, when the platform was placed on top of the soda cans, allowing the platform to move, then you could get spontaneous synchronization. So the tendency would be individualistic behavior when there's weak interaction, synchronization when the interaction is powerful enough, and somewhere in between, unpredictably very often, there will be this abrupt phase transition to a new form of organization, to spontaneous synchronization. And I mean, what that bridge example shows too is that, think of those poor engineers who were so embarrassed by their bridge doing this unexpected thing. I mean, if they had tested the bridge with 150 people on it, they would have seen nothing. They would have thought the bridge was fine. It was only with 160 that it suddenly started moving. So these are very difficult phenomena to predict in complex systems. As a general rule, though, if you wanted to avoid synchronization, as in the case of the bridge, you need some mechanism of damping the vibrations, which in this case meant redesigning the bridge by putting shock absorbers underneath it to absorb the vibration. And so if you walk on the Millennium Bridge today, even with a big crowd, it will not wobble anymore. Damping is one way. Now, the other thing, though, is that you can also increase diversity among the individuals. If the people had different walking speeds or different sensitivity to the motion of the bridge, you could also disrupt the synchronization that way. And so that's going to be a general theme for us, that greater diversity can oppose synchronization in the cases when you want to oppose it. Now, Thinking about even more real-world examples than this case from civil engineering, you might think of the case of the stock market, where imagine a financial market to be somewhat like the bridge, and an individual investor is like a pedestrian. As the pedestrian or the investor decides to buy Bitcoin or whatever popular stock, they move the market a little bit, which is like the people moving the bridge a little. And so you can get, under certain circumstances, herd behavior in the markets where everyone is buying and selling at the same time because they're moving the market and the market is acting back on them. There's also the phenomenon among organizations where sometimes everyone starts to think the same way about difficult challenges, and you have the psychological phenomenon of groupthink, usually very undesirable. The remedies are to promote more diversity, different opinions, different ways of looking at things, or you could reduce the interaction among people. You may have heard the phrase wisdom of the crowd. It's often said that the crowd can make better decisions collectively than the individuals. But the crowd is only wise if the crowd doesn't communicate. If the crowd is in sync and is obeying groupthink, it's not going to work. You need independent-minded crowds in order to have the wisdom of the crowd. All right, so let me move on to my second example, which is something that we're all experiencing nowadays. We, of course, have real social networks in our lives, but we also have these online social networks that it's hard to resist. I notice people checking their cell phones, probably their Facebook status is being updated as we speak. Let's look at Facebook because it holds some interesting general lessons. I want to focus on one particular counterintuitive phenomenon, which is the so-called friendship paradox, which says that your friends are probably more popular than you are. Now, that will not be true of every person. There are some people who are so extremely well connected, they are more popular than their friends. But the claim is that on average, your friends will be better connected than you are. And that will be true for most people. It sounds impossible, but it's true. Now, let me show you some data to indicate that it is true, and then also I'll give you a little explanation of why it's true. Facebook was studied as a set of points connected by lines that is a mathematical network for the first time in 2011. That was a while ago now, and at that time there were 721 million users, which was about 1/10 of the world's population. That number is now closer to 1/3 of the world on Facebook. So it's a substantial fraction of the whole world. The interactions among those people, whereby I mean Facebook friends, there were, at the time, 69 billion Facebook friendships among those 721 million people. And so we can ask, are people likely to have more friends than their friends do, or not? The finding was that if you looked at the size, if you ask users, or actually what nobody was asked, the computer scientists just measured this. These were people working for Facebook. They measured how many friends a typical user had and also how many friends the typical friends of that user had. And the finding was that 93% of the time, users had fewer friends than their friends did, on average. So in other words, only 7% of people were so well connected that they could defeat the friendship paradox. 93% of the people it applied to. Another way of looking at it would be like this. What's the average number of Facebook friends that the users had? 190, it turned out, at that time. On the other hand, if you look at the friends of a typical user, they had 635 friends of their own, just in line with what the friendship paradox says. So I'm sure you're thinking, this doesn't make any sense. I don't really see how this could be true. Let me try to illustrate how it could be true with an example that my children drew. At my request, I asked them to draw a very small social network consisting of 4 girls. And you'll see at the top is Abby, who has only one friend, the social butterfly Becca, who is in the middle and who is friends with everybody. And then at the bottom, and by the way, I'm organizing these A, B, C, D, in case you're wondering about the names. At the bottom, on the left, Chloe has 2 friends. She's friends with Becca and with the 4th girl, Deb, who also has 2 friends. So if we calculate for this little network, what's the average number of friends? As you can see, Abby has only one friend, Becca. Becca has 3 friends, and Chloe and Deb each have 2, and if we take the average of those numbers, it comes out to 2. 2 friends on average. Now, let's do the same calculation, except rather than asking what's the average number of friends, we ask each person to consider her friends. How many friends do those friends have? So take a look. Look, for instance, at Abby. Imagine asking Abby the question. She's the one on the top. Abby, how many friends do your friends have? She would say, I only have 1 friend, Becca. Becca has 3 friends. Ask the same question of Becca. She would say, well, I have a friend, Abby, who only has 1 friend. And I have these 2 other friends, Chloe and Deb, and each of them have 2 friends. And so on. So you can ask these questions of everyone, and when you add up the number of friends and average it, you get 2.25, a little bit higher than the average number of friends itself. And you can see the reason. It's because of this social butterfly, Becca. Her 3 has gotten counted 3 times. Right? Look at the calculation. She is friends with so many people that she gets named a lot as a friend, and then her 3 gets counted that many times. And so what's happening in the friendship paradox is that the highly connected people are being weighted more heavily than the average person. Now, why does this matter? I mean, it seems like just a little numerical trick, but in fact, it has very serious implications for the world in the context of contagion. If we think about something spreading on a network, now what could spread on a network? All kinds of things can spread on networks. Diseases can spread, but so can extremist ideologies, so can failures of banks, so can blackouts in the power grid. I mean, we need to think about things that spread on networks in the modern world. Consider, for instance, the case of the flu. The flu is very contagious. Back in 2009, there was a pandemic of the so-called H1N1 flu. And researchers at Harvard did a study in which they asked whether they could use the friendship paradox to provide a kind of early warning system for outbreaks of contagious disease. The way they did the study was, first, they asked undergraduates at Harvard, how are you feeling? Have you gone to the health clinic to see if you might have the flu? Have you done a search for the symptoms of the flu on your social, on Google or anything else? Basically, what is your flu status? Do you think you might have the flu? So they asked the undergraduates what their flu status was, but they also asked the undergraduates to name some of their friends. Then the researchers asked those friends the same question. How are you feeling? Do you have the flu? Have you gone to get checked for the flu? And the finding was that the friends, in fact, got sick 2 weeks earlier than a typical random undergraduate. Now think about why that would be true. If the friendship paradox is correct, and it is, it means that the friends of a typical undergraduate are probably more connected in the social network sense, and also in the disease contact network sense. And so they are likely to come in contact with the flu sooner because of their many connections. And this is a very significant effect that by monitoring, public health officials should keep this in mind, that if you wanted to monitor a disease outbreak, you could do it by, rather than just assessing individuals, ask individuals who their friends are, and then measure the friends. The friends will be an early warning system for a disease that would not be detectable if you just measured individuals themselves. So in addition to being an early warning system, this can also help us prevent the spread of a contagion. For instance, if you wanted to immunize a network, a good strategy would be, of course, if you knew who the most highly connected people were, you could just immunize them. In the case of some sexually transmitted diseases, that is, like, for instance, gonorrhea, there are people who are known as super spreaders. The super spreaders are often sex workers, prostitutes, in other words. They have a lot of contacts. And removing them from the network would be a good way to stop the spread of gonorrhea. On the other hand, many networks have the property that people like to stay hidden. I mean, the prostitutes are not announcing themselves as prostitutes. And so if you need to find highly connected nodes in a network that wishes to remain invisible, And you can probably think of other networks with this characteristic, where there would be important, highly connected members who don't want to be known. A way of finding those highly connected people is to find normal, random people and then get them to give up some of their friends. And those friends will tend to be more highly connected than the random individuals. So if you immunize or vaccinate the random friends of friends, that will be a better way of stopping, basically causing herd immunity in the population. So it's not a strategy that has been tried widely as far as I know, but it could be very effective. Now let me go on to my third example, and this has to do with the phenomenon of urban segregation. It was an issue that was very much on the minds of people in the United States in the 1960s when the phenomenon was called white flight, that white people would move out of inner city neighborhoods as black people moved in. You could imagine all kinds of examples today with tribes that don't want to be near each other, or it could be races, it could be religions. We have this issue of segregation in many different parts of society. So the question was looked at by this great social scientist, Thomas Schelling, in a 1971 paper. He was studying racial segregation. It gave us the phrase tipping point. I notice people speak about tipping points. This is a mathematical concept that grew out of Schelling's work on segregation. He later went on to win a Nobel Prize for this and other work that he did in economics. But what I want to show you is his model of segregation. It's extremely simplified, not realistic, but it makes the point, somewhat the way the metronomes do, about how much is to be learned from studying these simple idealized examples. To illustrate Schelling's model, I want to show you a simulation of it made by Vi Hart, who is a mathematician, and Nikki Case, and she is a computer scientist. They call it the parable of the polygons. The individuals are going to be shapes. So take a look. Here's a small set of our shapes. We've got the blue squares and the yellow triangles, and you can see their facial expressions. Some of them are unhappy and some are happy. Now, what makes a shape happy is it likes to be near its own kind. Blue likes to be near blue and yellow likes to be near yellow. But these are actually fairly tolerant individuals. They are perfectly content to be in a mixed neighborhood. If you look, for instance, at the yellow triangle at the top, you see its smiley face. It's cool with having two blue neighbors. That's fine, because it also has two triangle neighbors also. So it's in a 50-50 neighborhood, right? It's not in the minority in its neighborhood. What makes these individuals unhappy is, on the one hand, if they are outnumbered, like look at the unhappy blue squares, well, each blue square has only yellow neighbors. It doesn't like that. It would like to have some other blues nearby. And so that's the rule in Schelling's model, that if you are in the minority of your neighborhood, you would like to move to somewhere where that's not the case. On the other hand, don't think of these as, I shouldn't use the word racist. Let's use the word shapist. These are not very shapist individuals in that they actually like to be near others who are different from them, as long as there aren't too many. All right, so they just don't want to be in the minority, but they're perfectly comfortable being next to others unlike them, as long as they're not outnumbered. Now, watch what happens if we ask, what would it take to make all the blue happy? Here's a little simulation. You'll see that some of the shapes are rocking, and that's because they're currently unhappy. So I start moving them around and see what will it take to make everyone satisfied. You still see that there are two that are not happy. Finally, everyone is content, except the system has spontaneously segregated itself. You might conclude, if you saw this society, that these are very shapist individuals who can't stand being near anyone different from themselves. But that's not really true. Look, for instance, at the upper left triangle. You see that it has no expression on its face. It's not happy or sad. And that's because of the rule I mentioned earlier, which is that Schelling's shapes don't actually want to be surrounded by their own kind. They like a little bit of diversity. That's why the smiling triangles are happy. They have some blue neighbors and they have some yellow neighbors. They want a bit of both, so they're not out and out shapist. They're just don't want to be in the minority. And meanwhile, though, I mean, the surprising outcome of this is that even though they only have a very small individual bias, the only way to make the whole society happy is to segregate it very extremely, which seems peculiar because no individual is that extreme in their desire. Here's what happens at the societal level. If we look at a much bigger simulation and let everyone start moving, again, look at the red curve going up. This system is spontaneously segregating itself. That's what it took to get everyone happy, except now it's 80% segregated. But if we make one small change in our society and say, please have some small preference for diversity, if you're 90% surrounded by your own kind, that should make you unhappy too. And then watch the society now desegregates itself. Just a tiny nudge, if there were just some incentive to favor being around others a little bit different from yourself, you get a society that spontaneously goes to a much happier outcome. So Schelling took this lessons from it. He said that he thought that people's interactions could lead to results that were neither intended nor expected. And he was astonished by them, but he also started to think that they were obvious the more he thought about it. And I would like to leave you with the idea that the big message of his work is that just a bit of diversity can have a huge impact in reducing segregation and possibly promoting greater social harmony in all sorts of ways. Thank you very much.